So welcome all to this webinar. Before we start, I want to briefly introduce our guest, Hanne Notø. And Hanne Notø is a DEEPICE PhD student at the Utrecht University, and she's studying to develop a method to associate the continuous flow analysis to the proton mass spectrometry. This will be so useful for the analysis of organic compounds in the ice cores. And she just spent a month here at Foscari University in Venice for her secondment. And she worked very closely with Elena Barbaro to learn the fast liquid chromatography method. And she worked on two alpine ice cores, one from the Grand Campaign and the other one from the Weisspitze, to analyze basically the levoglucosan. And the premises of her results are really encouraging. So I don't want to waste any more time, and I will let Hanne present herself and her interesting project.
Yeah, thank you so much. Thank you, Jessica. So as mentioned, my name is Hanne, and I'm originally from Oslo in Norway, but now I study in the Netherlands at Utrecht University. And yeah, my project is a part of the DEEPICE project. And we also, in my project, have collaboration with Tofwerk, which is a company in Switzerland, as well as the Foscari University in Venice. And yeah, today I'm just gonna present about my project. First, I'm gonna talk a little bit about DEEPICE and also Beyond Epica, the drilling project that's going on in Antarctica right now. And then I'm gonna move on to explaining a little bit what information we can get from organic compounds in ice and why it is interesting and important. And then I'm going to describe the PTRMS technique, which is the instrument that I'm using the most in my PhD. And then I'm going to talk a little bit about what I've been doing in the past month that I spent in Venice. So that's the plan for this presentation. So Beyond Epica is I'm sure most of you know already, but it's a drilling project that's going on in Antarctica right now. And it's a collective effort from European countries. And the goal is to retrieve the oldest continuous ice core from Antarctica. So in the past, they drilled the Epica core, which took us back about 800,000 years. But now the goal is to find even older ice that could be up to 1.5 million years. And the period around 1 million years ago includes the mid-Pleistocene transition, which is important to have a look at because that's when the glacial, interglacial phases on Earth changed from a 40,000 year cycle to a 100,000 year cycle. And we're not really sure exactly why that happened. So finding that part of the ice is essential, and we could learn a lot from looking at the oldest part of the ice, because at the moment we don't have that good methods to look at the climate 1 million years ago. So that's the aim of the Beyond Epica project, and since it's really expensive to drill this ice core, they want to exploit it as much as possible and get as much information out of it as possible. And that is why, yeah. So here we have some photos from the drilling. They've been there for one drilling season and got down to the end of the Fern core. And now in the upcoming drilling season, they'll be drilling the ice and hopefully getting the oldest ice in about 3 or 4 years, I think. And here we have another photo of the crew with the Fern core. So yeah, it's really exciting to see what's going on there, and I would recommend looking at their blogs when they're drilling, because it's really fun to keep up with. But yeah, so the goal is to get as much information as possible out of the core, and that is why the DEEPICE project got started. So the DEEPICE is an innovative training network, which is the goal is to train 15 early stage researchers in climate change and glaciology, and especially, figuring more out about Antarctica and yeah, seeing what we can learn from the core from Antarctica about the whole global climate. So yeah, we're 15 PhD students. We're located in 10 different countries and 11 different institutions. And here you see a map of where we are. I am located here in Utrecht. And yeah, I spent a month in Venice, which I'll talk a little bit more about later. So yeah, we're quite spread out in Europe, but we do have some meetings and training schools as a part of the program. So yeah, it's really nice to be a part of this group. And yeah, we have a lot of different training schools because the goal is to like train the next generation of ice core researchers. So we're doing these different training schools in like analytical, statistical, and modeling. Like they have different themes. So the goal is to like train us as well as possible so that we learn as much as possible in the 3 or 4 years that we're working in DEEPICE. So yeah, it's really nice. And here's a picture of the group. This is quite an old one, so the group has changed a little bit. But yeah, this is most of us at least. So yeah. And so why are we looking at Antarctica? Here's a nice little figure of what ice cores can tell us. So I'm sure most of you know already, but in Antarctica, there's been snow and ice for several million years. And since it's so cold, it doesn't melt during the summer, or at least not to a significant degree. So the snow just layers on top, and then more snow like falls next year, and then the snow underneath gets trapped and preserved. So we basically have this like fingerprint of the past atmosphere that's trapped in the air bubbles in the ice. And also there's like dust and particles that is trapped in the ice. And that's more specifically what I'm looking at. So here on the left side here, we see it says from dust to past changes in the environment. And that's basically what I'm looking at, like dust and dissolved organic particles that are in the ice. And I'm going to tell you a little bit why. But first, I'm going to explain a little bit what I'm doing. So my sort of project description is thermodesorption PTRMS for measuring organic compounds in deep ice. Sounds a little bit complicated, but I'm going to break it down. So the PTRMS is an analytical instrument. I'm going to discuss it a little bit more later. But the thermodesorption part was developed at Utrecht University. And so far, it's mainly been used to study nanoplastics in environmental samples. And we study them in different matrices. So we've analyzed a lot of like aerosol filter samples to look at particles in the atmosphere. But also more recently, there's been more studies on snow and like plastic particles that are deposited in remote areas. So we're kind of looking at the atmospheric transport and where do these plastic particles end up depositing, and how do they get there? So that's kind of what we can learn more about. But of course, the PTRMS can be used for many other particles, and is very good for organic compounds in general. We can study hundreds of compounds at the same time, which makes it a really useful method. But anyway, the goal for my project is to use the PTRMS to study ice, and I want to like measure the ice continuously. And that's been kind of difficult because the PTRMS only takes gas phase samples, but I want to inject liquid samples. So what I'm doing is developing a sample introduction system because the liquid sample needs to be evaporated before it enters the system. So that's what I'm working on. And then after I finish developing the sample introduction method, I will validate it on some ice samples. And then, yeah, the goal is to couple the setup with the a CFA system that is in Venice. So that means that we'll be continuously melting the ice core. So we have these sticks of ice, and then we're slowly melting the ice from the bottom, and then the meltwater goes directly into the instrument. So there's no sample preparation involved. Everything is directly analyzed, which really helps out with these low concentration organic compounds, because we reduce the risk of contamination, and it's overall just better, I think, to analyze it directly. So that's the sort of main goal of my project. But what are the organics in ice, and where do they come from? So there are several, like, both natural and anthropogenic sources of organics in ice cores. So the main natural ones that I'll be looking at are tracers of biomass burning. But there's also some that I have a bit of interest in from volcanic eruptions, and also from marine biogenic, like marine biology in general. There are some organics that are emitted from algae and plankton. So that could tell us a little bit more about what was happening in the oceans in the past. And there's also volatile organic compound emissions from plants. And that's been measured a lot in forests. And yeah, it could be interesting to see if we find any of those tracers in the ice from Antarctica, as it's quite far away from forests. And also in the more recent years, we also have a lot of anthropogenic effects. So these are compounds that come from combustion engines, so mainly diesel and gasoline combustion. Also a lot of, like, organic pollution from industry. And there's a whole array of different compounds that are put into the atmosphere and can be transported. Also, there's a lot of VOCs, volatile organic compounds, from residential wood burning. And we see more and more pollution problems with that in urban areas. And lastly, also generally from agriculture, there are a lot of emissions, but especially when like the agricultural waste is burned, or when they burn off forests to create pastures and so on, that creates a lot of emissions. So these are the main, like, sources of organic compounds that I expect to find in the ice cores. And yeah, so as I kind of mentioned, I'm looking more specifically at tracers of biomass burning marine organisms, especially phytoplankton. A little bit about volcano eruptions, and then sort of linked to the marine organisms is tracers for sea ice extent. I'll explain that a little bit later. But yeah, and then lastly, also the anthropogenic impacts in the top layers of the ice from Antarctica. And that's basically what I'm looking for in the ice. So specifically, what compounds are we looking for? Well, in general, quite a lot of them. There's a lot of organic tracers for these scenarios, but these are some that I've been looking more closely at. So as the tracers for biomass burning, we have vanillic acid, syringic acid, and levoglucosan that are probably the most interesting. They have been studied a bit in the past, but not too much. And at the Foscari University, you also have a method that I've been working with now for the past month that can detect all three of these. So yeah, these are some really interesting compounds to look at, because they are quite specific to biomass burning, and they're not really produced in any other way. So here's a table from an article written by Rubino and coworkers. So as you see, there are some inorganic and, like, ions that are used for biomass burning tracers. And you see that in the column on the left, but these have more than one source. So they're not very specific to biomass burning, but the column in the middle shows the compounds that are specific to biomass burning and don't have any other sources. And as you see, all of these compounds are organic, and that's why they're interesting to measure, because they don't have any other sources. So if we see these compounds, we know that it comes from biomass burning. And for the marine biosphere, so for example, phytoplankton, we have specifically methane sulfonic acid, or MSA, that I've been looking a bit at. So phytoplankton in the ocean produces dimethyl sulfide, DMS, which then turns into MSA quite quickly. And that's why MSA can be used as a tracer of phytoplankton in the ocean. So the MSA we can see in the ice is related to the activity of the ocean around the location that we're looking at. So this is a compound that I'm really interested in looking more into. And then, of course, we have a lot of anthropogenic compounds that are only emitted quite recently. So some of them are persistent organic pollutants, POPs, that's quite a general term. We also have some PFAS, polyfluorinated alkyl substances, and micro and nanoplastics that have been really under the spotlight recently. So there's more and more literature on plastics in remote areas, and that's also a large part of the research that has been done in my group has been done on nanoplastics. So there's a large amount of compounds that we can detect, and it tells us a lot about different sources of pollutants and yeah, where they came from. So why is this important? Well, it tells us a lot about the past events in Earth's history, such as large forest fires, phytoplankton blooms, and as well as sea ice extent around Antarctica. And learning more about this will assist our understanding of the climate system as a whole. And since organic compounds are mainly linked to the biosphere, it can give us a fuller picture of what has happened in the past. And the chemistry of an ice core can really tell us about which source that the organic compounds come from, which is why organics are a unique tracer and a great tool to determine different sources of airstreams and just what has been happening in the past, because we don't really know much about it. And it's great because organic compounds are very source specific, so that makes them really useful. But of course, there are some limitations, such as the low concentrations of organics in ice. And let's see. Sorry. Okay, so I'm gonna talk a little bit more about the instrument that I'm using. It's called a PTRMS, or for short, which stands for proton transfer reaction mass spectrometry. And it's a chemical ionization technique because we ionize the sample with protons, or with the hydronium ions, H3O+. And that makes it softer than the traditional electron ionization. And this is very useful because the sample is more preserved and it's less fragmented, which means that we can better see which compounds that we're looking at. So it's been mostly used for the analysis of gas phase organic compounds, mainly in like air pollution studies, or just to understand the trace gases in the atmosphere. But now I would like to use it for liquid samples, which I'm gonna discuss. What's nice with the PTRMS is that it samples continuously, so you can do a measurement and have one mass spectrum every 1/10 of a second, so like 10 mass spectra per second, which is really fast. Or you can even increase the sampling rate. So that makes it nice to study really small changes in concentrations of organics and quick changes in the atmosphere. So that's why it's been used so much for ambient air measurements. And also a really nice thing about the PTRMS is that the main components of air are not detected. So that means like nitrogen and oxygen and just the components that are found the most of in air we don't really see. So we only measure the trace gases that are organic, which is really useful. And here is a photo of the instrument. It looks like this. This one is open, so you see all the wiring inside, but down here you see the inlet. This is where the sample is introduced, and then it goes into the PTRMS, which I have a photo of next. And then this is the computer we use to log the measurement, as well as to have a look at the measurement while we're running the sample. And the inside part of the PTRMS looks like this. So on the left side, you have an ion source where we produce hydronium ions. And then the hydronium ions are introduced to the analyte in the drift tube, which is here, where it reacts and transfers its proton to the analyte, which is then ionized. So then afterwards it's introduced to the mass analyzer, which in most cases is a time of flight mass spectrometer. But yeah, so this is the basic principle of it. I'm not going to go too much into detail, but what we end up with is a positively charged analyte, which we can then later detect. And here we have a close-up of the thermal desorption part. So this is actually the sample introduction part. So you can't really see it that well, but we have a glass vial in here, where the sample is located. In this case, it's a dried saltwater sample, so from the ocean. And then what we do is supply clean air into the vial, and then it picks up whatever is in the sample, and then the sample is introduced into the PTRMS. And meanwhile, we're measuring this continuously. We're heating up the bottom of the vial to thermally desorb the compounds that are the semi-volatiles that are left in the sample. So that's like the basic principle of how it works. So we have the heating at the bottom, which releases some of the compounds that are then transported into the PTRMS. And this method has been mainly used for nanoplastics in different matrices. But yeah, so we've mainly researched nanoplastics in, this is from seawater samples. Here there are some measurements from polar ice. And then we also have some filter samples. So that's like atmospheric aerosols, and looking at nanoplastics and microplastics in atmospheric aerosols. So that's what it's been used for the most so far. And what I want to do is use the same principle for the organics in ice cores. So this is something I presented at EGU in May. So what we did was take some alpine glacier samples and analyze the organic aerosols or the semi-volatiles in the glacier snow. So we had a closer look at nanoplastics, but we also found a lot of microplastics in the samples. But yeah, so basically what I would like to do is go from the thermal desorption PTRMS and then modify it to make a liquid evaporation system, which takes not discrete samples, but continuous samples of ice. So I've been testing it out a bit, and I'm going to show you next how it looks. So this is the basic principle of it. We have the continuous liquid sample that's making droplets onto a heated surface, which then evaporates the sample and then transports the gas phase sample into the PTRMS. Because the problem is that the PTRMS only takes gas phase samples. So we need a way of going from a liquid flow into a gas flow. So this is the basic principle that I would like to get working. So far it's been going all right. But yeah, the idea is to have the CFA of the ice core. So the ice core would be slowly melted, and then the meltwater goes directly into this flow. And then it's continuously evaporated and goes into the PTRMS for analysis. So that means that none of the sample is wasted. We just like directly sort of evaporate the sample into the instrument. And what I've done so far is that I had a secondment in Switzerland, where the idea was to test out how well this method could work. Yeah, I tried developing some sort of sample introduction interface, did some tests there. And then what I also wanted to do is test the sensitivity of the instrument to the different organic compounds that we're interested in the ice. And it went quite okay. I think it's going to work quite well. And what I'm doing now is more closely developing the evaporation system. So hopefully that will be done within the next few months, and then I can test it. And eventually I'll do some measurements using that system. And then next, I want to explain a little bit what I was doing in Venice. So as most of you know, I was there for 1 month. So from the end of May till the end of June. And the plan was for me to go there and learn how the LCMS works, because later on I'll be using it for the, in parallel with the PTRMS. So what I did was, learn a little bit how the LCMS works. And we also managed to analyze 2 ice cores, one from Austria and one from Switzerland. Yeah, it was a really good learning experience. So what I'm going to do next is to test the coupling of the PTRMS with the CFA system in Venice, and then run measurements in parallel using the PTRMS and the LCMS. Because the LCMS can measure only a few compounds at the same time, but the PTRMS has the advantage that you can measure hundreds of compounds at the same time. So I want to see if we get similar results with the PTRMS as the LCMS, and also what other compounds can we measure using the PTRMS compared to the LCMS. So it will be really interesting to test the connection of the CFA system to the PTRMS, and that's the main goal of my work moving forward. And what we accomplished in Venice was that, as I mentioned, we melted and analyzed 2 ice cores. So we did continuous measurements of specifically levoglucosan in the ice cores. And as you see on the bottom left, here are some of the data. So we have these little spike injections every 30 seconds. So that's the resolution of the measurements is every 30 seconds. So that's equivalent to every 1 to 2 centimeter of the ice core. So we did that. It took a bit of time to melt and analyze the ice cores, but we were a big team doing that, and it was really nice to be a part of. And then afterwards, we had a lot of data to analyze. So what I did was make a script to integrate the peaks that you see in the bottom picture, because there was no automatic way to do it. So I wanted to make a script to integrate the peaks automatically so that we wouldn't have to click and drag the peaks because we had hundreds of them. So that's what I did, and it's been working quite well. And here we have some very preliminary data from the measurements. So this is from the Weiße Spitze ice core in Austria. It's, as I mentioned, very early stage, but we see some peaks, especially this huge one is really interesting. It goes up to almost 60 ppb of levoglucosan. And then we have some smaller peaks as well. Of course, this needs to be more, have a better chronology, and we still have a lot of work to go with this, but so far it looks really interesting. And the median value of the median concentration of levoglucosan in this ice core is about half a ppb, and that's quite similar to one other ice core one other paper I was looking at from. They measured an ice core in Russia, in eastern Russia, and they reported quite similar values of levoglucosan. So that's really interesting. And as far as I know, this is the first continuous measurement of levoglucosan in an ice core. Please correct me if I'm wrong, but I think it's the first continuous one. So that's really exciting. And it's been really nice being able to do this in Venice. So what I'm going to do next time I come is bring the PTRMS, and then I will connect it to the CFA system. And the goal is to run the measurements in parallel. So measure the organic compounds on both the LCMS and the PTRMS at the same time. And this will give us a lot of useful information about the organic compounds in ice. And then, yeah, so I'll bring the PTRMS and we'll analyze a new ice core, and then we can compare the results. And it's also nice because then we can expand the number of organic compounds that are detected continuously in an ice core. And so far in research, there's not that many continuously measured organic compounds in ice. Most of them are in discrete samples, so it will really improve the resolution if we can detect organics using CFA. So that's the goal. And moving forward in my project, I'm going to, as I mentioned, develop this method. So this will allow for the continuous analysis of organic matter in the ice cores. So what I'm going to do next is finish the evaporation system. It's currently being built in the workshop, but hopefully it'll be done within the next few weeks. And then I can do some tests with it at Tofwerk and test it with their setup. And then later on, I'll bring it to Venice. So yeah, the goal is to couple the CFA system to the PTRMS. And then, of course, I'll have to optimize the instrument to get the best sensitivity to the compounds that I'm most interested in. And then later on, I'll have to validate the method on the ice samples, which is going to be done in Venice. So that's the plan for the next few months or years in my project. And I'm really looking forward to it. So that's the goal. And that's basically all I wanted to say. And with that, I just want to thank you all for the attention. And yeah, let me know if you have any questions.
Hi, Han. I would have a question, if you don't mind.
Yes, of course.
Yeah, first of all, thanks of all for your work and for being here in Venice. We have been very, very happy to have you here. So again, you are more than welcome with the instrument to couple it with the CFA. And my question is exactly on that point, on the coupling the CFA to your mass spectrometer. What do you think would be the most difficult thing? Flux, the whatever.
I think that's a great question, first of all. So I think the most difficult part will be, well, I thought it would be getting the right flow that I need for the instrument because I need quite a small flow with the setup I'm building. It's only about 15 or around 20 microliters per minute. So that's very little compared to a lot of other methods. And it's hard to have a stable flow of that small magnitude. So I thought that would be the hardest, but being in Venice and talking to Azzurra, for example, it was clear that that wasn't that much of a problem. But now I think the biggest challenge would be to have a good enough sensitivity of the compounds of interest. So it varies a bit from PTRMS to PTRMS, so they're not all built the same. So some instruments have a good sensitivity for some compounds and other instruments have better sensitivity for other compounds. So I think choosing the right type of instrument and also tuning the settings will be a lot of work, and trying to figure out the best way to measure as many compounds as possible, but with high sensitivity. I think that's going to be the most challenging part.
Super. Finger crossed. Thank you.
Yeah, thank you.
I just wanted to thank Anna for her seminar, and I ask to my colleagues if are there other questions.
Excuse me, you hear me?
Okay.
Yes.
I'm Helena, and I wanted to thank Hanne for her very, very excellent work in the group during the cold melting week. She performed a very excellent work together, and also she developed a very nice Python program to integrate. So I want to thanks a lot Hanne for her work.
Thank you. And thank you so much for having me. It was really
also,
nice.
And also for the photo from Burano, my island.
Yes, yeah, it's so beautiful there. Thank you so much.
Other questions?
Yes, I do. This is Tomato Tesi from Bologna. Can you further, and first of all, thank you for your talk, really nice and really clear. And could you further elaborate on the use of lignin as a proxy for fire? Because lignin is everywhere. If you think of pollens, that you might have in, lots of in ice core, I suppose. How can you distinguish between different sources of different change in vegetation? Especially for pillar reconstruction, you go from different vegetation. So I'm wondering how you can be so specific with lignin as a proxy for fire.
Yeah, thank you for the question. So yeah, of course, lignin is in a lot of different plants, but yeah, so there are some differences in the combustion products between plants that mainly consist of lignin and plants that consist of cellulose mainly. So I don't remember exactly. I've been looking more generally at biomass burning, but yeah, there are some differences in the compounds that are produced in the combustion of lignin plants versus cellulose plants. So I don't remember specifically at the moment, but there is some research done on this. And also different temperatures of fires produce different volatiles. So there we can distinguish a little bit between the types of fires just by looking at specific organic compounds. I don't know if that helps much, but yeah.
Right, thank you.
Are there other questions? So I don't read no more questions in the chat. So I want to thank again Anne for her seminar, and to thank to my colleagues for their participation. Thank you again.
Thank you so much.